Okay, good morning, everyone. Maria, can you hear me?
Yeah, I can hear you. Can you hear me? Okay.
Let's see, is Maria here yet?
I am.
Maria, let me know if you can hear me.
I just sent you a message.
Can anyone hear me?
We can hear you.
You can hear me.
Okay, maybe there's a problem. So if anybody can hear me, speak up.
We can hear
If
you.
not, I may need to restart my Zoom.
I can hear you just fine. Professor Long?
Okay, all right, I see in the chat that everyone can hear me. Thanks. Sorry about that. And so I hope everybody has found accommodations and is okay sheltering in place. This is a pretty unusual time for everyone, and we realize it's difficult for students, so um, we did cancel last week's lecture, and also we're delaying the due date for the problem set. It'll be the Tuesday after spring break. And I want to remind everyone that I know a lot of people might not have great Wi-Fi connections at home, but we are recording these sessions. So hopefully if you have difficulty seeing the live lecture, you can go and watch the recording. And before we start, are there any questions or issues anybody wants to bring up on how the class is going to be handled? As I think everybody knows, we're going to have remote Zoom lectures for the rest of the semester. We are figuring out a system where you'll be able to take the exam at home and then scan and upload your results. Exactly what we'll use and how we'll do that, we'll let you know after spring break. But any questions on procedure for the Zoom lectures or other issues? Okay, if not, I'm going to start. And let me remind you, if you have questions, please, you could raise your hand, and I should be able to see that and call on you. All right, great. So remember,
Can you hear us?
yeah, I can hear you. Thank you. I was wondering about that. Okay, so last lecture we just started thinking about electron transfer reactions. So these are reactions where one metal center is transferring an electron to another. And we noted that there can be two types of reactions. They can proceed through an inner sphere mechanism, which involves formation of a covalent bridge between the two metals, or an outer sphere mechanism where no covalent bridge is formed. The two complexes diffuse together, and electron transfer proceeds through an outer sphere hopping pathway. And so, of course, in general, if the electron transfer is faster than ligand substitution, then the reaction will follow an outer sphere pathway. The inner sphere pathway necessitates ligand substitution to form the bridged intermediate. Oops. Okay, so here are some data. These are reactions similar to the cobalt 3 chromium 2 inner sphere reaction we looked at previously. But all of these reactions involve cobalt 3 complexes, and the reductants can be chromium 2 aquated, europium 2 aquated, or vanadium 2 aquated. And you can see here the rate constants can vary widely. So here we're seeing 11 orders of magnitude difference for cobalt 3 being reduced by chromium 2. And you can see that the rate is really following very much whether or not there's a good bridge forming ligand on the cobalt center. So for cobalt trisethylene diamine and cobalt hexammonia 3+, neither of those ligand types can form a good bridge with any of the reductants, either chromium, europium, or vanadium. And so presumably those reactions would have to proceed through an outer sphere mechanism. And so those are the slowest rates that we see here. And then water and nitrates can form bridges, but they're not very good bridging ligands. And so they show faster rates, but not the fastest of the series. The fastest rates are seen for the bottom 3 complexes, where a halide ligand is very well suited to form a bridge to the chromium, europium, or vanadium center and enable the inner sphere pathway. And so particularly for chromium 2, you can see these very fast rates, suggesting a very different pathway for the electron transfer. And generally, for similar metal ion complexes, an inner sphere electron transfer reaction will go faster than an outer sphere one. That's not to say that you can't have fast outer sphere electron transfer, but if there is a similar combination of metals and bridge formation is facile, that will usually speed up the electron transfer reaction. All right, so now let's think about distinguishing mechanisms here. And we're going to particularly focus on this reduction of a cobalt 3 complex containing ammonia and chloride ligands with chromium 2. And let's just look at the differences for what we'd expect for inner sphere versus outer sphere pathways, right? So, so the reaction is going to be between this cobalt 3 complex and chromium 2. And we've already seen what the products of that reaction will be. But for an inner sphere, assuming an inner sphere electron transfer mechanism, we'd expect the first step to be those 2 complexes diffusing together in solution, forming a bridged, chloride bridged intermediate. Right? So no electron transfer has occurred yet. You form this bimetallic chloride bridged species. And then the next step would be electron transfer. So here, electron is moving from chromium 2 over to cobalt 3. And that results in chromium +3 and cobalt +2. And once that electron transfer has occurred, let me point out, so this initial complex where we haven't done the electron transfer, that's called the precursor complex. And then the species that you get after, immediately after the electron transfers, this would be the successor complex. And once you form the successor complex, then we can note that now the lability has changed. So initially, cobalt-3 is inert and chromium-2 has labile ligands. But after the electron transfer, that situation is swapped. Now chromium-3 is inert and cobalt-2 can substitute ligands rapidly. And so this is noted here. So that cobalt-3 chloride bond is inert in this precursor complex, whereas the chromium chloride bond is labile. But in the successor complex, that situation has switched. And so after electron transfer, then chromium-3 is going to be, because it's inert, it's going to retain the chloride ligand, whereas cobalt-2, which is labile, will shed its ligands, including that bridging chloride, and form an aquated species. So water can displace the chloride. The chloride remains coordinated chromium-3. And then the final step would be the ammonia ligands on the cobalt-2 substituting to give us the hexa-aquo cobalt-2 product. Right? And of course, so the overall products are this chromium-3 with the chloride attached and this cobalt hexa-aquo complex 2+. So the fact that chloride has transferred from cobalt to chromium, this is suggestive of an inner-sphere mechanism. But let's assume that instead it was going by an outer sphere mechanism. The steps here would involve the two species diffusing together, and then electron transfer occurring without any change of the ligand sets. And so here we're just doing right off the bat in this species where we've got the two molecules next to each other, electron transfer will occur, and we'll create this cobalt-2 pentamine chloride species and the chromium-3 hexa-aquo cation. And the next step then would be cobalt-2 rapidly losing its ligands owing to its lability, and will form the cobalt-2 aquo complex and release chloride into solution. And then we know our product should have the chloride bound to chromium-3. And so the final step would have to be a ligand substitution reaction where chloride substituted for a water ligand on chromium-3. And of course, we know chromium-3 is inert, so this last reaction we expect will be extremely slow. In fact, that reaction, that rate has been measured, and the rate constant associated with that particular reaction, which is called anation reaction, it's been measured at about 3 × 10⁻⁸. So this is very slow, and it's much slower than the actual overall rate of this electron transfer reaction. So the observed rate for this reaction is about 13 orders of magnitude faster than the anation reaction rate for chromium-3. And so this is strongly supporting then that it must be going through an inner sphere mechanism rather than the outer sphere mechanism. Okay, any questions on that? If you have a question, feel free to speak up. All right, if not, we'll keep going. All right. So another piece of evidence here that's extremely supportive of this inner sphere pathway is is simply adding, if we add into this reaction some isotopically labeled chloride anion. So this is adding a chloride as a 36 chlorine isotope, which is a beta emitter that's readily detected, and it's easy to tell if you've attached it to your chromium product. And the observation is that if we start out with cobalt-3 having this non-labeled chloride ligand, the product that we get is entirely that non-labeled chloride. We see, unless you wait a very, very long time, you won't see any of this 36 chloride binding the chromium, right? And so that's indicative again of and very strongly supportive of an inner sphere electron transfer pathway here. Right, so no 36 chlorine incorporated. So taking these inner sphere, this inner sphere mechanism and considering it further, there are really 3 steps, as we wrote down for that example of reaction. And it's going to turn out that any one of these 3 could be rate determining for the reaction. So the first step is formation of a bridged intermediate. So the 2 complexes diffuse together, ligand substitution occurs to give the bridged intermediate or precursor complex, and that has a rate constant and equilibrium constant associated with the reaction or the step. Second step would be this electron transfer, and that's going to have a KET rate constant. And then the final step is dissociation of the successor complex to give products. And so this KD is going to have some rate. There's going to be some rate for dissociation of the successor complex, depending on the lability of this metal ion that's dissociating. As I said, any of these could be rate determining or rate limiting. And we can understand that if we look at a reaction coordinate diagram. And so here you see 3 different profiles for the reaction coordinate for the free energy of one of these reactions. And they correspond to cases where the first step being rate determining would be the left panel. The second one being rate determining would be the middle panel. And the right panel is the third step being rate limiting, right? And so for, if the first step is rate limiting, that means we're gonna have this big barrier to form the precursor complex. So the substitution to form a bridge species has a large barrier. This is the highest transition state energy on the coordinate, and it determines or limits the rate, right? And then once you form that precursor complex, it could be the case that electron transfer is very rapid, small barrier. And it could then be that it's very easy for the successor complex to fall apart. So for the second step, the electron transfer step being rate limiting, this is a very interesting situation. And this is one that we'll discuss in much greater detail next lecture. But yeah, so here the highest transition state energy is for transferring the electron, the reaction to go from the precursor complex to the successor complex. And that barrier can be high because, as we'll see, it might be that a lot of rearrangements of the ligand sphere are required to trigger electron transfer. And so this being the rate limiting step has a lot to do with what needs to happen for the ligands surrounding a metal in order for electron transfer to to proceed. And so, as I said, we'll go through that in great detail next lecture. But in this case, then the successor complex would easily fall apart. And then the final scenario is step 3 being rate limiting. So here, this third transition state is highest in energy. It's you're going to form the precursor complex, easily transfer the electron, but then there's another even larger overall barrier to dissociate the successor complex. Okay, so any questions on this? If so, go ahead and speak up. All right, if not, let's keep going. So let's just look at some situations where each of those scenarios is thought to be occurring. And so, we should note that if step 1 is rate limiting, then it should be the case that the rate of the electron transfer reaction will be similar to the rates of ligand substitution. And so here we have some examples where this appears to be the case. These are reactions where we're starting with cobalt-3, an inert complex. We've got 5 ammonia ligands, or ethylene diamine and ammonia ligands. And then there is, in each of these cases, a bridge forming ligand. So this is protonated oxalate. This is oxalate. This is azide, N3 overall 1 minus. These all have azide. And those cobalt-3 complexes are being reduced here by vanadium-2 and giving then vanadium-3 and cobalt-2 products. And so here you see measured rate constants under similar conditions for all of those reactions, and they're very, very similar. This is what you would expect for a case where step 1 is rate limiting. Right, it's always going to be a dissociative reaction, and it's going to be dissociation of vanadium-2 and then forming the bridged dissociation of water from vanadium-2 plus, forming the bridged intermediate via either oxalate or azide. And then the subsequent steps must not be rate determining. And so here we can see part of the reason that this makes sense is also that this is really pretty much the same rate at which vanadium-2 does ligand substitution reactions. So if we look at, for example, water displacing a water ligand on vanadium-2, this has a rate constant that's a little bit faster than shown for these reactions, but very similar. If we take, say, thiocyanate and do a substitution reaction on vanadium-2, we see a very similar rate for the reaction as to what we're seeing here. So this is highly suggestive of this dissociative ligand substitution at the vanadium-2 center to form the precursor complex being the rate limiting step. Right? And you can see thermodynamic parameters measured for these reactions as well. Okay, if we have a situation where step 2 is rate limiting, then we would expect that the actual overall reaction rate might be very sensitive to the nature of the bridging ligand, right? So if that second step is rate limiting, then the details of the electron transfer reaction for the precursor complex going to the successor complex, that's going to dictate the overall reaction rate. And so here are just some example rates for reactions where here we have cobalt 3 plus, 5 ammonias, and an anionic carboxylate ligand. And we're just going to vary L along this series. And the reductant here is chromium 2. And we're going to form cobalt 2 hexaquo complex. And the ligand L is going to be transferred to then the chromium center in our chromium 3 product. So you can see you can organize these in order of increasing rate constants as we go down top to bottom here. And so benzoate is slow, glycolate at the bottom is fast, relatively speaking. And these all correlate with how easy it is to add an electron to these various species. And so to some degree, the ease with which an electron might move between metal centers through a bridging ligand can be associated with how easy it is to add an electron to that bridging ligand, right? And so that's the pattern that's seen here. So the lower barrier for glycolate would be associated with glycolate being easier to reduce compared to, say, benzoate. So that's just one factor that could influence this electron transfer rate for the second step in an inner sphere mechanism. We'll look at a number of other factors next lecture. When step 3 is rate limiting, then you'd expect this is going to be a situation where electron transfer has resulted in both metal centers becoming inert. And if that electron transfer creates species that are inert, then you have a very good chance of even isolating this successor complex as a pure molecular compound. And so here's an example of that. So we're starting with ruthenium 3, 5 ammonias, chloride, and it's being reduced by chromium 2. Chromium 2 easily and rapidly loses water and allows chloride to form a bridged complex. And so this reaction is fast. The electron transfer reaction is then fast, but what's very slow is dissociation of this successor complex shown here, right? So after electron transfer, we've now got chromium 3, and that's going to be inert, so it doesn't want to dissociate. And ruthenium 2 as a second row metal, transition metal, is also rather slow to dissociate its ligand. And so you can, as a result, this product persists and can be isolated in pure form. Okay, that's, as I said, you can often isolate the bridged species. All right, so it turns out that closely related to the study of inner sphere electron transfer reactions is the study of what are called mixed valence compounds. And so we're going to now take some time and consider mixed valence compounds. And a mixed valence compound is simply one where you have a metal center that is present in the compound in two different redox states, at least two redox states. So it's going to be the same metal, but the oxidation state is not just, say, all 2+ or all 3+. You might have some of the metal centers being 2+, some of them being 3+. So we saw, for example, that magnetite has a mixture of iron 2 and iron 3, and that's a very good example of a mixed valence compound. So there's a very key classic paper oops, from Melvin Robin and Peter Day. This is from 1967, and this is really it's a long paper. It's a very comprehensive review at the time of mixed valent compounds, but it set up a really important classification scheme, recognizing the differences between different types of mixed valent compounds that's still very heavily used today. And so the focus in this article is really on extended solid materials. So it's mostly solids. There's some molecular examples. But we're going to go through the classification scheme that they devised with this paper. The paper is available on our course website. And I encourage you to take a look. It's long. You don't need to read it all. You can see here it's 150 pages or so. But it's a great resource if you encounter a mixed valent compound and want to understand its nature and compare it with other compounds. This is a good resource. All right. So this is then known as the Robin-Day classification scheme for mixed valence compounds. And the crux of it is that Robin and Day said that a compound containing at least two metal sites with different oxidation states linked through some bridging moiety can be classified according to the degree of mixing between the two states shown here. Right, so we're going to have some lowest energy state with energy E naught and wave function psi naught. And it's going to correspond, so here M, this is going to be the same metal in the periodic table. But one type of metal site in the compound has an X plus oxidation state, and the other has a Y plus oxidation state. And then you could imagine transferring an electron, or maybe multiple electrons, to swap the oxidation states at the metal centers. Right. So now the left hand, this type of site is Y plus, this type of site is X plus. And associated with that state would be some energy, generally higher in energy, E1, and some wave function psi1. So the situation is for mixed valence compounds, if these two states are similar or close in energy, then they could mix. And we classify mixed valence compounds by the degree of that mixing between the two states. And so here we've set it up so that E naught is lower in energy than E1. So delta E will always be greater than or equal to 0. So of course, if delta E is 0, then you have degeneracy, and it means the two states are completely mixed. And that's going to be what we call a delocalized state. And so the actual wave function for the system we can write as a mixture of psi naught and psi 1, depending on this mixing parameter alpha. So alpha is the key parameter saying how much of psi 1 is mixed in with this ground state psi naught to give us the overall ground state, or this lower energy state psi naught to give us the ground state. And so the coefficient in front of psi naught is just, as written here, square root of 1 minus alpha squared. And these values simply come out of normalization of the wave function, right? So, you know, this is a normalized form, but the magnitude of alpha then is going to be associated with the degree of mixing of these two states. And we classify them then according to Robin and Day's scheme. First of all, for class 1. Class 1 is a situation where the oxidation states X and Y are fully localized. And there's a large energy gap before you get to the Psi1 state. And therefore, there's essentially zero mixing. All right, so a large delta E, large energy difference between E0 and E1 means that there's little chance of electron transfer, that electron transfer E1 state being part of the ground state. And alpha should be near 0. Psi is essentially psi naught. The second case is going to be class 2, and this is in some cases referred to as a partially delocalized situation. And so here we've got delta E being greater than 0, but some energy less than 27,000 wave numbers. Then that means in these cases, alpha will be somewhere between a minimum of 0 and a maximum of 0.5. So if alpha squared is between 0 and 0.5. Alpha squared equaling 0.5 would be the case where you have equal parts psi naught and psi 1 in your ground state. And that is the situation for class 3. So here in class 3, you have a fully delocalized system where the oxidation state of the metal is actually best given as the average of X plus and Y plus. And in this situation, delta E will be 0. There's no energy difference. And this mixing parameter alpha squared will be 0.5, meaning, again, you have equal parts psi naught and psi 1. Right? And so this situation, for this situation to be true, if you think about it, it means that the coordination environment around mx plus and my plus should be identical. Should be very, so it should be the same geometry, the same ligand, such that when you do electron transfer, these energies can be the same. Okay, any questions before we continue? We're going to go through examples next. Yeah, go ahead. Hey, Jazzy.
Hi. Yeah, I was wondering if we have to consider symmetry at all when we consider mixing between these two energy states.
Yes. So so mixing of states has to be allowed by symmetry, and so that is part of whether or not it occurs in addition to energy proximity. I think that was your question. The other place that symmetry comes into effect is if you have very different symmetries at these two different metal sites, then generally one oxidation state will prefer one of those compared to the other.
Thank you.
All right. Any other questions? All right, so let's just go through each class and some examples, and we'll do an example both from extended solid compound and a molecular species. So first up, we've got class 1, large delta E. So you'll note this value for delta E is really, so 27,000 wave numbers is a cutoff, and it's also the edge of the visible region of the spectrum. So for these class 1 compounds, if you did have an electron transfer between the two different metal sites, then that band would not lead to a colored compound. It would be in the UV region, very high energy, because those two different states, psi naught and psi 1, are very different in energy. And so this situation is common for compounds where you might have very different coordination geometries around the metals MX plus and MY plus. So very different ligand fields means that one of these oxidation states is going to prefer one of the sites over the other. Right? And it can also happen if you have bridging groups that are not very amenable to electron transfer. So perhaps you do have a similar ligand field at MX plus and MY plus, but there's no good pathway for the electron to move between the two metals. Right? So that would create a large activation barrier, and then you wouldn't see the localization of the electron. So general properties, there are some general characteristics that we could expect for compounds of this type. And so first up, there's going to be a visible transition for the metal-to-metal charge transfer, right? So MMCT is metal-to-metal charge transfer. That would be transferring electron through this gap delta E between psi naught and psi 1, right? If that's very high energy, delta E is larger than 27,000 wave numbers, then we wouldn't expect a color to be arising from this MMCT band. And the color would simply be the color that you'd expect based on the color of the individual metal ion centers, right? It would be, the UV vis spectrum would be just a summation of the two individual ion spectra. Generally, these compounds would not have magnetic coupling between the metal sites. If the metal sites have unpaired electrons, there wouldn't be strong coupling, and you wouldn't see a transition to ferromagnetism, for example. And they'll usually be electronically insulating, right? If there's not electron transfer happening, then you wouldn't expect electrical conductivity. And so let's go to a couple of examples. First example will be cobalt 304, which is a spinel type compound. And so spinel is actually a mineral which is has the formula MgAl2O4. And so this cobalt oxide has that structure type. And it's a complicated structure. So we're going to take a look at some solid state structures here for examples of mixed valence compounds. And if you don't remember some of the rules about structure types, you could go back and review what you learned in Chem 104A. Spinel has a formula AB2O4, right? And here you're seeing a unit cell depicted for that compound. But A and B are two different metal sites, and the A site has a tetrahedral coordination of the oxide O2 minus anions, and the B sites are octahedral in coordination. They have an octahedron of 6 O2 minus oxidoanions surrounding them. And the way these are built into the spinel mineral structure is, here's the repeat unit. And so the black spheres here are the tetrahedral A metal sites, and the cross-hatched spheres are the B octahedral metal sites. And then the open spheres, the white spheres, are oxide O2 minus anions. And it's a complicated structure, so you should study this a bit and try to make sure you understand how it's put together. but it's a face-centered cubic unit cell, right? So you have this A cation in the center of each face, as well as at the corner of each corner of the unit cell. And then the octants of the unit cell have occupancies that look like as shown here. So in 4 of the octants, you have an A-type situation where you have this tetrahedron, this AO4 tetrahedron in the middle here. And so those A octants are located front, bottom, left, back, right, rear, front, top, right, and back, rear, top. And then the other octants have this occupancy that looks like this. So one of them is shown here. And you should convince yourself if you stack these unit cells together, then the B metal cation will indeed have an octahedral coordination geometry. Right. So the Spinel structure, if you want a more simplified description, one is given at the bottom. But this structure, you can think of it as a cubic closest packing of oxide anions with the A2 plus cations in 1/8 of the tetrahedral holes of that packing, and the B3 plus cations in half of the octahedral holes in that packing. So recall from 104A, we often describe these solid state structures based on the packing of the anions. The anions are generally larger. Remember, the radii of an anion is generally larger than the radius of a cation. And very often you'll get a closest packing, either cubic or hexagonal. In this case, it's cubic of those anions. Those closest packings will lead to tetrahedral holes and octahedral holes. And not all of those holes are filled, just a certain portion of them with these cations A and B. So in the cobalt oxide spinel, both A and B sites contain cobalt. And cobalt 2 plus prefers the tetrahedral site, whereas cobalt 3 plus is on the octahedral site. So this is a situation where cobalt 2 plus, if we were to do an electron transfer from the tetrahedral to the octahedral site, that's a major difference in ligand field, and that's going to be a very different energy, right? So if you try to transfer an electron, it's going to be a large energy gap, very different structure, very different energy, and therefore this compound is mixed valent, is a class 1 mixed valent. So the cobalt oxide spinel then, if we look at its, its color and visible spectrum, it's what you'd expect for tetrahedral cobalt 2 oxide or combined with octahedral cobalt 3 oxide. So it's simply this combination of those two spectra. Okay, so for molecular example, there are lots of possibilities here. Essentially, any molecule where you have two metal centers with different oxidation states, but the bridging ligands are something that is fully saturated and not compatible with electron transfer. And so, for example, if you had a bridging ligand where you had amines and the two amines, one binding each metal, and connecting those two amines were saturated, a long saturated alkane chain. That we would expect to give rise to a class 1 mixed valence compound, because there's a big barrier for transferring the electron through that saturated diamine bridge. Okay, any questions on these class 1 compounds? If so, speak up, please. Yeah, go ahead. Last name Huang.
Is the bridging angle will the bridging angle affect the electron transfer rate?
Yes. Yeah, actually the exact geometry of the bridge connecting the metals and the orbitals along that bridge will very much influence the electron transfer and the degree of mixing between these states. And so in the next class 2, that will become a little more evident.
Thank you.
Other questions? All right, so let's proceed to class 2 then. All right, so class 2 is a very interesting situation where the energies of the states are close and they can mix to some extent. And we're interested in evaluating and understanding the degree of mixing, this parameter alpha. And we can do that from spectra. We can extract alpha from the UV visible, sometimes near IR spectra. And in this class, we have ligand fields that are not very different. So that we would expect when you transfer an electron and swap the oxidation states, there's not going to be a big energy difference between those two states, right? And so that's necessary such that the two states are close in energy and can mix. So we need to have a situation here where we don't have big differences in ligand fields or geometries. And we also need this second criterion of bridging ligands that are amenable to electron transfer. The properties that are seen for these class 2 compounds, usually and importantly, you can find a metal-to-metal charge transfer band. Often it's going to be this delta E energy in the visible region. And as a result of this additional band, the spectrum that you see will not be just a sum of the spectra for the individual ions. Rather, there'll be this additional peak corresponding to the MMCT band. And since that's in the visible often, this compound will have a perhaps surprising different color compared to the individual ions. In this case, owing to the possibility of communication of the electronic structures at the two metals, we can see some magnetic exchange in many cases. And for conductivity now, a lot of the extended solids of this class 2 variety are going to be semiconducting. So they have some degree of electronic conductivity. So let's go through a couple of examples. First example will be a really old compound known as Prussian blue. The formula you can see here, it's a cyanide bridged compound. We'll look at the structure in a minute, but it has iron 2 and iron 3. So you can see there's a 4:3 ratio of iron 3 centers to iron 2 centers. And then there's a lot of water in this structure as well. And this is it's a very old compound. It's been known for more than 300 years. And it's a very simple reaction to make this compound, but it's very striking when you produce it. And so here's a video showing Prussian blue being made. So the colorless solution here is a solution containing ferrocyanide, FeCN6 2 minus, or rather 4 minus. So it's the potassium salt of ferrocyanide. It's colorless. And the liquid that's being added, the yellow liquid you see here, that's an aqueous solution of iron 3. And those react to form this brilliant blue solid precipitate. Right? And so it's this really formed very little of this compound. It has this intense blue color. And this is actually one of the first synthetic dyes that we produced. And it's been used in dyeing fabrics and in paintings by artists for centuries now. And so it's known as Prussian blue. And so just some examples, you can see here, this is a very famous painting. A lot of you have probably seen it, but this is a painting called Under the Wave off Kanagawa by the Japanese artist Katsushika Hokusai. And it was painted about 1830. But the really stunning blue color for the waves here is coming from the Prussian blue pigment in the paint. You can see, you know, here are the poor people in the boats and Mount Fuji in the background. So another example, this is a famous painting you've probably all seen. Anybody remember the name and artist here? Go ahead, Amy.
Starry Night by Vincent van Gogh.
Exactly, yeah. So the blue colors that Van Gogh used here in his oil painting is containing Prussian blue. So you can see lots of Prussian blue in this painting, and this is about 1889. So the previous paper with the wave off Kanagawa was, the previous painting was about 1830. This was about 1889. Actually, Prussian blue as a paint started being used around 1700, it's thought. And initially it was made not in this nice, simple process that we just saw, but it was actually made using pig's blood as the source of iron, and a much messier process. Okay, so let's take a look at Prussian blue in a little more detail. So the reaction that we just saw is formulated at the top. So iron 3+, aquated iron 3+, we're adding it to that color. So this is the yellow solution. We're adding it to that colorless solution that contains these octahedral FeCN6 4- anions. And what's happening is the nitrogen end of cyanide, those atoms, those nitrogen atoms, are displacing water in the coordination sphere of iron 3+ and making these bridging interactions, these linkages, where we're going from iron 2 to carbon to nitrogen, iron 3. And so in the product that you get, this is just the unit cell. It's a face-centered cubic unit cell again. And the red spheres are iron 2, and the green spheres are iron 3+. And the cyanide, the carbon end of cyanide is bound to iron 2, whereas the nitrogen end of cyanide is bound to iron 3. Both metal centers, both iron 2 and iron 3, have an octahedral coordination geometry. But of course, the carbon end of cyanide has a slightly different ligand field from the nitrogen end of cyanide. In particular, it has a much greater overlap for the pi star orbital of the ligand with the metal. So slightly stronger ligand field around the iron 2 as a result. So you'll note in this structure, it doesn't actually match the formula at the bottom, right? Because this structure, if you count up the number of iron 2 and iron 3 sites, it's a 1-to-1 ratio, right? But in the formula, it's a 4-to-3 ratio. So Prussian blue actually has defects, and the defects correspond to missing ferrocyanide, FeCN6 4- units. And those vacancies are missing, generally depending on how you make it. The missing ferrocyanide units are disordered throughout the lattice. And so on average, these FeCN6 sites are occupied only 75% of the time, right? And the vacancies that are created by those missing ferrocyanide units, they're filled with water. And so water, you can see there's a lot of waters, 14 waters per formula unit, depending on humidity. So water fills the pores that you see in this material, as well as the vacancies from the missing ferrocyanide units. All right, so as I said, there are 25% of those FeCN6 4- units are missing from the lattice. So relevant here, this is an example of a class 2 mixed valent compound. The energy difference here between the states that are mixing are about 15,000 wave numbers. And that's what's giving rise, this metal-to-metal charge transfer across that gap delta E is giving this intense blue color. Right? So the blue color is based on the position of this band. And the intensity is actually given, it's associated with the degree of mixing. So an important point here is that we can, it's beyond what we're going to do here, but you can extract from the extinction coefficient for this MMCT band, you can actually extract a measure of that mixing parameter alpha. So here, from that band intensity, we get an alpha squared of about 0.01. Right? But this is quite a lot of intensity, and it's giving rise to that really brilliant blue color. Of course, iron 3 complexes with this ligand field are very weakly colored and probably yellow. Ferrocyanide is colorless, has a large band gap. This compound also has some magnetic exchange interactions, and it becomes a ferromagnet at low temperature, down at about 3.5 Kelvin. And it also is intrinsically a semiconducting material. So that's consistent with the properties that we expect for a class 2 mixed valent compound. Okay, any questions on Prussian blue before we continue? All right, if not, let's keep going. So for a molecular example, a nice example for these mixed valent molecules, very often we can use as examples these diruthenium complexes, where at each end you have ruthenium coordinated by 5 ammonia terminal ligands, and then some bridging molecule connecting the 2 ruthenium centers, and overall a 5+ charge state, meaning that on average each ruthenium is 2.5+. So we've got 1 ruthenium 2+, 1 ruthenium 3+. So for this 4,4' bipyridine bridge, you can have a little bit of a twist between these two pyridine rings. And so this is a case where there can be electron transfer, but the mixing of the states is going to be weakened because this is a rather large bridge that's not always conjugated, providing an electron transfer pathway. So we'll look at more examples of this. For a class 1 compound, as I was saying, if instead of bipyridine you had, say, a saturated hydrocarbon backbone connecting the nitrogens, that would provide a very poor electron transfer path and a class 1 compound. All right, yeah, so here are some other bridging ligands in the same kind of construct. So again, overall, we've got one ruthenium-2, one ruthenium-3. Here's the bipyridine bridge that we just discussed. This is showing the distance between the metal centers. This is the metal-to-metal charge transfer band energy, delta E. And then this is the extinction coefficient, how intense that band is. And that's going to correlate with how big alpha, the mixing parameter, is. So we get an intensity here of close to 1,000 for bipyridine. If we put methyl groups on the pyridine rings, the sterics of those methyls cause the pyridine rings to prefer not to be coplanar. And that drops the intensity because it's weakening the mixing of the two states. And therefore, we have a less intense metal-to-metal charge transfer. If we put a saturated group, this methylene spacer between the two pyridines, this is essentially an insulating barrier, and you can see that band intensity gets really small. This is very close to what might be considered a class 1 compound. If you have an ethylene double carbon-carbon double bond between the pyridines, this can provide a conjugated pathway. Oops. So here, even though the metals are further apart, we can get this stronger mixing of the states. And here's an example. If you add another carbon-carbon double bond into the ligand, this is even easier to reduce. You have a more accessible orbital pathway. Even though the metals are further apart, you get greater mixing and a more intense MMCT band. And then at the very bottom, you see these sulfur-based bridging ligands. And these are quite poor at transmitting electrons. And you can see the longer those get, the weaker the mixing between the states. Okay, so finally then we have class 3 mixed valence compounds. And this is going to be the situation where the two different metal sites are having identical ligand fields and have bridging ligands that are very amenable to electron transfer. Properties, we expect that the spectra will be not just the simple spectra of MX plus compounds plus MY plus compounds. Rather, it's going to be some new spectrum associated with the average valence metal center. And often these have ferromagnetic ground states. If they have unpaired electrons, then you can get very high ordering temperatures. So an example of this is actually magnetite, right? So magnetite is a good example. And in terms of electronic conductivity, these tend to be metallic compounds. So often you'll see they have a metallic sheen, and they're very good at conducting electrons, of course. All right, so some examples here. First example will be what's called a sodium tungsten bronze. So this is this tungsten oxide where you can, depending on how you make it, you can introduce varying levels of sodium. So X here can vary, for example, between 0.3 and 0.9. And as you increase that value for X, you start filling up a conduction band within the material, and the color dramatically changes. So here is before we discuss these further, let me point out that these compounds have what's called the perovskite structure. And so here's a unit cell for a perovskite. You may have discussed perovskites in Chem 104A. But perovskite, the name comes from the mineral perovskite, which is calcium titanate, so CaTiO3. But in general, there are many compounds that have this structure type, and we have two different cations: a large cation A and a smaller cation B, and then an anion X. And so you can see here in this unit cell, the small cation B has an octahedron of surrounding anions X. Right? And then if you stack these together and extend the structure, you get something that looks like this. So this is 8 unit cells stuck together. The colors are slightly different. Green spheres are still the A cation, blue spheres are the B cation, and the red spheres are now the X anions. And so you can see here how the octahedral metals are forming this cubic network of corner-sharing octahedra for the MX6 octahedra. And the A cations, so one of them is right at the center of this cube, they have 12 coordination with a cube-octahedral coordination environment. So one way of describing the perovskite structure is that it consists of a cubic closest packing of the anions X and A cations. So the larger atoms in this compound are going to be the X anions and these large radius A cations. So those together form a cubic closest packing. And then the B cations occupy 1/4 of the octahedral holes, right? So you can see they're octahedrally coordinated, particularly by the anion. So the sodium tungstate compounds, those sodium tungsten bronzes, the blue atoms will be tungsten, the red atoms will be oxygen, and the green spheres will be the sodium cations. And for those compounds, the cation A site is only partially occupied, right? You can see that from the formula here. It's X is going to be less than 1. But this is just showing, you know, with low numbers of X, you actually get a distortion into a tetragonal structure. But these are really stunning compounds. If you ever see large crystals of these compounds, they're really beautiful because they're metallic. They have metallic reflectivity like silver, but they also have that combined with a very intense color. And so these with small x have their metallic blue colored crystals. As you increase X and start to fill up that conduction band with more electrons, you go across the visible. So here's violet, metallic violet colored crystals, metallic red crystals, orange, and yellow. So these are, especially if they're nice, large, well-faceted crystals, really fascinating to look at. And so these are also, of course, very, very conductive materials. And oh, you should note, as we change X, we're changing the oxidation state of tungsten. These compounds have a mixed valence of somewhere between tungsten. So if sodium, if X were 0, then the oxidation state of tungsten would be +6. If X were 1, then it would be +5. And so for these compounds, tungsten has an average oxidation state of somewhere between +5 and +6, depending on X. And all of the tungsten centers are equivalent here, and the electrons are delocalized equally between all of them. Okay, so another example of one of these class 3 mixed valence solids would be silver fluoride, Ag2F. So in this compound, you have fluoride 1- anions, and the silver cations are all identical, and they all have a +1/2 oxidation state. And so the structure here is what's called the anti-cadmium iodide structure. And it's a layered structure. So here's a depiction of two of the layers. And within layers, so the white spheres here are cadmium 2+ cations. They're surrounded by an octahedron of iodide anions shown in gold. And those octahedra share edges to form two-dimensional sheets. And then you have a van der Waals plane between sheets. So these are this is a two-dimensional material before you have another layer with cadmium. So anti-cadmium structure. So actually, first of all, this structure you can describe it as having a closest packing of anions, hexagonal closest packing in this case. So you can see the AB ordering. And the cadmium 2+ ions are occupying half of the octahedral holes to give this layered structure. So anti-cadmium iodide, anti means that you would swap cation and anion positions. So in silver fluoride, you have Ag ½ on the sites where you had iodide, and fluoride minus is on these octahedral sites where there was cadmium. Okay, and then just to finish up, a last example here we've already looked at last time, but the Kreutz-Taube ion, which has the pyrazine connecting the two ruthenium centers, this is by many probes showing a class 3 mixed valence situation. And that's because the pyrazine is extremely good at enabling electron transfer between the ruthenium centers. Okay, so we're out of time. Actually, we have time for one question, if anybody has a question. If so, go ahead and speak up. Otherwise, I realize it's not going to be the typical spring break, but try to enjoy next week off, and I'll see you the following Tuesday, or at least I'll be speaking to you the following Tuesday. All right, bye everyone.